Okay, event 1 is to flip the coin and then spin the spinner. Part A, list the 10 outcomes in the sample space. The first one has been done for you. So our job is to go through and just list out what could happen. So they've done, let's see, they could flip a heads and then have a spin of a 1. Well, we could flip another heads, but get a spin of a 2. We could heads 3, heads 4, heads 5, heads 6. Just kidding. There's only 5 on the thing. So that's the entire sample space just for flipping a heads. Now we have to go through it for tails. So for tails, we could flip a tails, flip and get tails. And then we could spin a 1. We could get tails again, spin and get a 2. Sorry, the battery is dying. Tails and get a 3, tails and get a 4, tails and get a, oh, there's an extra spot, that's why I'm throwing off, tails and get a 5. So that's our entire sample space. So this one does not need to be filled in. Okay, they're letting event A be that the coin comes up heads. Event B is a spinner lands on an odd number. So the probability of getting event A, so the coin coming up A, would be 1 out of the 2 options, or 0.5. Make sure you don't give a percentage unless it specifically asks for a percentage. You can either reduce the fraction or give the decimal. Find the probability of B. So the spinner lands on an odd number. Of the 5 options, so that means it could spin and land on a 1, a 3, or a 5, which is 3 out of the total 5 options for the spinner. So we can reduce, or not reduce the fraction, but convert that into a decimal, which would be 0.6. So again, either the reduced fraction or the decimal. Part C, does the coin flip affect the spinner? No. So flipping the coin does not affect the spinner. Therefore, we say that events A and B are independent events. Okay, part D, multiply the probability of A times the probability of B. So that would be 1/2 times 3/5, which would be multiplied, multiply fractions, we multiply across. So 1 times 3 is 3, 2 times 5 is 10. So it'd be 3 out of 10, or 0.3. Part E, look at the sample space and find probability of A and B. So if I'm figuring out getting coin coming up heads and the spinner landing on an odd number. So out of the flipping a heads, we could, let's see, we could spin a 1, spin and get a 1, we could spin and get a 3, or we could spin and get a 5. So those are the 5 possible, what's that? 5 possible outcomes. So that would be 3, well, that's the 3 possible outcomes. Sorry, I said 5. 3 possible outcomes out of the 10 possible values in our sample space. So that matches up with what we just found. So that would be 3 out of the 10 in our sample space, which would be 0.3. Okay, part F, does the probability of A and B equal the probability of A times probability of B? Yes, it does. If so, this is evidence that A and B are independent. So that's how mathematically we prove independence when we're given the scenario where we have A, we have B, and we have A and B. Okay, if not, then we know the 2 events are not independent. So if those were not equal, if we didn't get 3/10 and 3/10 for both of those, then they would be not independent, or you could say they are dependent. Okay, event 2, we spin the spinner 3 times in a row. So now we're adding like a sequence to it. Part A, find the probability that you get these three spins, a 2, a 2, and a 2. Well, spinning and getting just a 2, so the probability of getting a 2 is 1/5. So the probability of getting a 2 and then getting another 2 and then getting a third 2, we're just going to multiply 1/5 times itself 3 times. So 1/5 times 1/5 times 1/5. Or we could have done that as an exponent, knowing that it's the same thing 3 times. So we might get to that later. So 1/5 times 1/5 times 1/5. Let's go ahead and make a note. That's the same thing as 1/5 to the power of 3, which would be equal to 1/125. Or as a decimal would be 0.008. Okay, part B. Find the probability that you get no 2s in the 3 spins. So not getting any 2s, meaning I could get a 1, I could get a 3, 4, 5. So not getting a 2 would be 4 out of 5. Because if one option is 2, that means the other 4 are not 2. Sorry, I have to try to fix this pen. Not 2 is 4 out of 5. Okay, so not getting 2 for the 3 spins would then be the same thing, the probability of not 2 and not 2 and not 2. So that would be the same as if we did 4/5 times 4/5 times 4/5, which would be 4 times 4 times 4 is 64, or 4 cubed is 64. 5 cubed is 125. 64 over 125 as a decimal would be 0.512. I went to 3 decimal places here just because I went to 3 decimal places in the last problem. Okay, part C, find the probability that you get at least 1 2 in your 3 spins. So we get, let's see, at least 1. So that would be 1 minus the probability of not getting any 2s. So, because that's a scenario of I getting no 2s. So if I figure out the complement of that, so that would be 1 minus the probability that I get no 2s in the spin, or in all 3 spins. And that was what we had found before. So instead of saying no, we could say not. So no 2s, and that's where we had gotten the 64 over 125. So we would do 1 minus 64 over 125. Because if I'm doing the complement of getting no 2s, that would mean at some point I get a 2, whether that's the first spin, the second spin, or the third spin. So to subtract these fractions, I need to, or you should just do the decimal, but I would make this into 125 over 125 minus 64 over 125. So we have common denominators. I do 125 minus 64, and that is 61 out of 125, which is equivalent to 0.488. It was probably safe to use that decimal because I hadn't rounded any of my decimals up to that point. Okay, part D. Changing the event slightly here. What is the probability that the first time you get a 2 is on the 8th spin? So that means for the, well, there's 7 spins in a row where I'm getting no 2s. So this is where the exponent comes into this. So no 2s, we just multiplied 4/5 times itself for however many spins. So I could do 4/5. Oh my goodness gracious. 4/5, more space. The eraser isn't erasing. There we go. 4/5 raised to the 7th power to represent that I spun the spinner 7 times and I didn't get a 2 any of those times. And then the last time I do get a 2, and the probability of getting a 2 is 1/5. So 7 spins of no 2s, and then on the 8th spin, I get a 2. So let's work this out mathematically. We figure out, really help if the eraser worked. 4 to the power of 7 would be 1,600, or sorry, 16,384. Makes sense. All divided by, and so multiplying that times 1, it's still the same thing. And then we have 5 to the power of 7. So 5 to the power of 7 would be 78,000 times another 5, because we're multiplying by the 1/5, would give us 390,625. Then I would reduce this fraction, or not reduce this fraction. Don't try to waste your time doing that. We're just going to change it to a decimal. 625. So I do that division and I get 0.042. We'll keep it with 3 decimal places. So it gets into the idea of, well, we know the and probability is multiplying. So if we're just doing this event over and over and over again, we're just going to multiply those probabilities together. And repetitive multiplication is an exponent, or is a power. Okay, event 3, we flip the coin 3 times in a row. So now we're focusing in on the coin. Part A, list the outcomes in the sample space. So we're flipping a coin 3 times in a row. Maybe we get heads all 3 times. Maybe we get tails all 3 times. Maybe I get heads, heads, tails, or I get tails, tails, heads. Maybe I get heads, tails, heads. Maybe I get tails, heads, tails. And last scenario, I could get heads, tails, tails, or tails, heads, head. Okay, so those are all the possible outcomes of flipping the coin 3 times. Part B, find the probability of A. So that's flipping the coin. All 3 flips come up heads. So the probability of getting heads would be 1/2. So this would be 1/2 times 1/2 times 1/2, because there are 3 flips. So that would be 1/8. So, and that makes sense because all 3 flips come up heads would be 1 out of the total 8 options that we had listed in our sample space above. Oops. So I was looking at this up here. Nope, you're going to highlight the wrong spot. There we go. Okay, part C, find the probability of B. All 3 flips come up tails. So to get tails would be 1/2 times 1/2 times 1/2. Because the probability of getting tails is 1/2. This is an and, so I want tails and tails and tails. So we're allowed to multiply our probabilities, and that would also be 1/8, which again matches up because getting all tails is 1 out of the 8 options in our sample space above that we see up here. Okay, part D, since the probability of A and B equals 0, meaning I can't flip and have all 3 flips come up heads or all 3 flips come up tails. It either has to be heads or tails. A and B do not overlap. That is, events A and events B are called mutually exclusive. So I can't have 3 flips that are heads and 3 flips that are tails at the same time. You can even break it down further. I can't flip a coin and get heads and tails at the same time. So part E, find the probability of A or B, which is the same as probability of A or B, just getting used to our symbols. That would be the probability of A plus the probability of B. And then we just said there is no probability of A and B. So that's going to be 0. because I can't flip a coin and get heads and tails at the same time. So the probability of A would be 1/8 we had found, plus the probability would be another 1/8 minus 0 would give us 2/8, or that is 1/4. Okay, so 1/4 or 0.25. So that would represent the probability of either getting all three flips as heads or all three flips as tails. Okay, event 4, we have spin the spinner 3 times in a row. Event A is all 3 spins are odd. Event B is all 3 spins are even. That's a typo. That should not say event. Okay. Part A, find the probability of event A, meaning we get an odd number, an odd number, and an odd number. So on the spinner, we have 1, 2, 3 odd numbers out of the 5. So this would be 3/5 times 3/5 times 3/5, because we're doing 3 spins. So that would be equal to 3/5 cubed. So 3 cubed is 27, 5 cubed is 125. So that would be equivalent to 0.216. Next, find the probability of B. So all 3 spins are even numbers. So we only have 2 even numbers on our spinner. So we can spin a 2, spin a 4. So that would be 2/5 times 2/5 times 2/5. So that would be 8/125. So 8/125 would be 0.064. Okay, part C. For the probability of A and B equals 0, because there can be no overlap between all 3 odd outcomes and all 3 even outcomes. So I can't spin the spinner and get a number that is even and odd. There's no way for both A and B to happen in the same 3 spin set. Part D, find the probability of A or B. So this would be equal to the probability of A plus the probability of B minus the probability of A and B, which we said that's going to be 0. So we have probability of A was that 0.216. Probability of B was 0.064. There is no A and B, so that's 0. So our probability for A or B would be equal to, which if I did the fractions, 27 plus 8 would be 35/125, or 0.28. Okay, first scenario, Jane is going to take a placement test and then apply for a job. So we have some different probabilities here. First one is event A. So Jane passes the test, and they're telling us the probability of Jane passing the test is 0.55. Second event B, Jane gets the job, and that would be a probability of 0.4. A and B would be that she passes the test and gets the job, which would be 0.35. Below, we need to match the notation. We need to draw a Venn diagram that matches a verbal description, and then find the probability. So A or B, nice color, A or B, see, that would match up with her passing the test or getting a job, or both. So this will eventually have to go down here. It doesn't really matter where we put the Venn diagram that goes with it. So let's go ahead and put it just down next to it, so that we know this matches with this. Maybe if the line will draw, and that this A or B is going to this Venn diagram. I don't think it likes when I'm low on the screen. Okay, so A or B, meaning I can have anything in circle A or anything in circle B. So it'd be A or circle B. So I should highlight or color in anything in circle A, or anything in circle B. And there's allowed to be an overlap between A and B. Okay, our next scenario, we have A and B. So that would be she passes the test and gets the job. So let's go ahead and put the Venn diagram right next to that description. So this is this would have to be the intersection where they overlap. So if we have circle A and we have circle B, I only want the area in between. So just in the middle there. Sorry, my highlighter doesn't go that small. And we'll go through the probabilities in a second. Third one, we have A and not B. So that would be event A is her getting passing the test. Not B would be not getting the job. So she passes the test, but doesn't get the job. So that actually goes A and not B. Actually goes right across. That's eventually going to go right here. A and B. So we want anything that shows that she passes the test and not getting a job. So that would just be this area, nowhere touching circle B, just circle A. So just this segment over here. Okay, and then our last one, right, there's only 4, I think. We have not, I didn't actually draw a line. That one goes right there. That's what I'm confused. Last one is not A and B, meaning she doesn't pass the test and gets the job. So that's our second option up here. That arrow is, that line is confusing. And gets the job. So we have circle A, circle B. So we want nothing in A and things only in B. That would be everything over here. So nothing in the intersection. Okay, you get the idea. Nothing in the intersection, just things in circle B. And that again. Okay, to find those probabilities, we're going to be using that notation and writing out those formulas. So the probability that she passes the test and gets the job. So that would be the probability of A and B. This would be equal to what they gave us above, 0.35. So we don't have to do any work when they give us that probability. Okay, our next one, fails test, but still gets the job. So that would be the probability of not A and B. So this would be equivalent to the probability of B, so the entire circle of B minus the probability of the intersection. So this would be equal to everything in circle B minus the part where A and B intersect, because I don't want that intersection, because I don't want anything in circle A. So probability of B was 0.4 minus A and B, they had told us was 0.35. So this probability would be 0.05. Okay, the next scenario, passes test but doesn't get the job. So that was our probability of A and not B. I can think about it the same way. I can take the entire circle A and subtract out the intersection where B gets in there. So this would be the probability of A minus the probability of A and B, because we don't know the exact breakdown of all of these. So the probability of A was 0.55. The probability of A and B is 0.35. Because I want everything in circle A, but I don't want to include that intersection. So that would be 0.55 minus 0.35 would be 0.2. Okay, then last one, either passes the test or gets the job or both. So this would be the probability of A or B, which would be equal to the probability of A plus the probability of B minus the probability of A and B. So the probability of A is 0.55. The probability of B is 0.4. The probability of A and B is at 0.35. So we do 0.55 plus 0.4. We get 0.95 minus 0.35 would give us 0.6. Okay, so just want to go over a visual of how to do those Venn diagrams and then using what we're given to find the given probabilities. Okay, scenario 2, pick one student at random from the following student bodies. So we have males and females and comparing if they're in 9th, 10th, or 11th grade. 9th, 10th, or 11th grade. Okay, so we need to figure out our totals. So there are a total of 20 9th graders, 20 10th graders, 20 11th graders, and 20 12th graders. And we surveyed 40 male and 40 female. So part A, the probability that they're in 9th grade or in 10th grade. So we'll do the probability that they're in 9th plus the probability they're in 10th. And can I have anybody in 9th and 10th grade at the same time? No, so I don't need to do the subtraction because they're mutually exclusive. It doesn't exist. So the probability that somebody is in 9th grade was 20 out of the total 80 surveyed. Plus the probability they're in 10th grade would be another 20 out of the 80 surveyed. Minus 0, because there's nobody in 9th and 10th grade at the same time. And that would be equal to 40 out of 80, which would be equal to 1/2 or 0.5. Okay, part B, the probability that they're in male or that they're a male or in the 9th, 11th grade. I can't read. So this would be the probability that they're male. We had 40 out of 80 males. Plus the probability that they're an 11th grader, that would be 20 out of 80 11th graders. Minus the probability that they're a male and an 11th grader. Sorry, I have to unscrew the pen and screw it back together. Helps with the battery. 20 minus male and 11th graders, there are 12 out of the 80s that are male and in the 11th grade. Okay, so we already have our common denominators. 40 plus 20 would be 60, minus 12 would be 48 out of 80. Which would that would reduce down to be 3/5 or 0.6. Okay, part C. Probability that somebody is in the female and 12th grade. So female and 12th would just be these 13 out of the total 80. And as a decimal, that would reduce down to be 0.1625. Okay, part D, they're asking for the probability that somebody's in a female or in the 12th grade. So that would be the probability that we randomly select a female plus, let's see, female was 40 out of 80. plus the probability that they're in the 12th grade. So 12th graders was 20 out of 80. Minus the probability that they are a female and a 12th grader, and that's that 13 out of 80 that we had identified before. So we do 40 plus 20 is 60, minus 13 would be 47 out of 80, which would reduce to be the decimal 0.5875. Okay, part E, are the outcomes female and 12th grader mutually exclusive? Yes or no? No, because there are 12th grade femalers that exist. A and B, we'll say. So there are 13 female 12th graders, 13 female 12th graders. Okay, part F, are the outcomes female and 12th grader independent? Yes or no? So we could check this out. So we said using our and formula. So let's see if the probability of female and 12th grader, and we want to see if that's equal to the probability of female times the probability of a 12th grader. I promise you, I'm not scribbling for fun. I'm just trying to erase all the bad marks. Okay, so we said female and 12th grader. We did this up here and we got 13 out of 80 or 0.1625. So if I did probability of a female was 40 out of the 80, which is 1/2. So we can do 1/2 times the probability of a 12th grader. That was 20 out of 80 or 1/4. And we want to see if we get the same thing as female and 12th grader. So that would be 1/8. 1/8 would be 0.125. So because those are not the same, they are not independent. So if they were the same, then yes, they would be independent. So I have to do the math to back that up. Okay, so quick recap of some of the formulas we've been using. So the probability of A and B is going to be equal to the probability of A times the probability of B if they're independent. So we'll also use that to prove independence. So you'll see sometimes in questions, it'll mention like, oh, these events are independent so that we know we can use this formula. Then our probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, which sometimes A and B will be 0. That just means that they're mutually exclusive. Okay, the probability of not A would be 1 minus the probability of A. So we just subtract out of our sample space the outcome that we don't want. And then our last one, probability of A given B, would be the probability of A and B divided by the probability of the condition, which was B. Okay, these formulas are used to prove independence. So probability of A and B equals the probability of A times B. If you do that multiplication and get the same value, then that proves they are independent. If you do that multiplication and get different values, like we saw in that last problem, they are not independent. If they are independent with conditions, the probability of A and B will just be equal to the probability of A, meaning the condition doesn't affect the probability of the outcome of A. Use these to prove that things are mutually exclusive. So A or B would be just equal to the probability of A plus the probability of B. Because if I'm using that OR formula that we had over here, referring to that, that would mean that A and B is equal to 0. So if you need to spell out 0, so you know it's not random O. Because it doesn't exist, so you could just do P of A plus P of B. So that's why we can abbreviate that mutual exclusive down. Okay, scenario 3. 50 individuals were asked 2 questions. Do you like the food at McDonald's? And do you like the food at Taco Bell? Okay, there we go. The results, sorry. The results include the following: 35 people like McDonald's, 30 like Taco Bell, and 12 people liked neither. So we need to first build our t-table based upon this information. So we know that 50 total people were surveyed, because they told us that in the beginning. Then they said that 35 people like McDonald's. So the people who liked McDonald's is 35. 30 like Taco Bell. And then 12 people didn't like either. So to figure out these values, we can use addition or subtraction. So if 50 total people were surveyed and 30 of them liked Taco Bell, that meant 20 of them did not like Taco Bell. And if 50 people liked McDonald's, or sorry, 50 people were surveyed and 35 liked McDonald's, that meant 15 of them did not like McDonald's. So now I can subtract from there. So 15 minus 12 would give us 3. 30, you can sort either way. 30 minus 3 would give us 27 people like McDonald's and Taco Bell. 20 minus 12 would give us 8 people who don't like Taco Bell but do like McDonald's. Okay, part B, organize the same information into a Venn diagram. So we had a total of 27 people like McDonald's and Taco Bell. So let's call this McDonald's. This can be Taco Bell. So 27 of them liked both. Then I had 8 people who liked McDonald's still, but didn't like Taco Bell. So there's an 8 out here. Of the 30 people who liked Taco Bell, we said 27 of them like McDonald's as well. So there are 3 people who only like Taco Bell. That leaves a remaining amount of, let's see, of the 12 people who don't like either of them. So they don't like McDonald's, don't like McDonald's. Okay, so we can check that our Venn diagram is correct to make sure that adds up to be 50. So 12 plus 8 is 20. 27 plus 3 is 30. 20 plus 30 is 50. So that checks out. Okay, find the probability of each. So the probability that they like McDonald's, so the total people who like McDonald's is 35 out of the 50 people surveyed. So that would be 35 out of 50 or 0.7. Again, you can do the reduced fraction as well. Next question, the probability that they like McDonald's given they like Taco Bell. So how many total people like Taco Bell? There were 30. Of those 30 people who like Taco Bell, just looking at this top row, 27 of them also liked McDonald's. So that would be equal to 0.9. Okay, number 3, the probability that they like Taco Bell. So there was a total of 30 people out of the 50 who liked Taco Bell. which would be equal to 0.6. And then the probability of T given M, so meaning given we know they like McDonald's, meaning there's 35 people who like McDonald's. Of these 35, 27 of them like Taco Bell. So we do 27 divided by 35, and that would be 0.77. Okay, number 5, the probability that they like McDonald's and Taco Bell. Well, that's the intersection of our Venn diagram. So that would be 27 out of the 50 people surveyed. So 27 out of 50 is equal to 0.54. Maybe if this lets me erase, there we go. And number 6, the probability that they like McDonald's or like Taco Bell. So we're going to do the probability that they like McDonald's plus the probability that they like Taco Bell minus the probability that they like McDonald's and Taco Bell. So liking McDonald's was 0.7. Liking Taco Bell was 0.6 minus the probability of liking McDonald's and Taco Bell, which was 0.54. So we have 0.7 plus 0.6 minus 0.54, and we get 0.76. Okay. Okay, number 7, from the information above, we can say with certainty that McDonald's and Taco Bell, well, so to figure out if they're independent or not, we want to figure out if the probability of M and T, you can either use the condition or the and formula. So we have both here. So does the probability of McDonald's equal to the probability of McDonald's given Taco Bell? No. So these are not independent. We know they are also not mutually exclusive because the probability of M and T is not 0. So had that been 0, we would have known that they would be mutually exclusive. So that's where I looked to make those distinctions. Maybe not. I guess we'll just leave it. There we go. Okay, scenario 4. Suppose that the following table represents a certain adult population. Let M represent those who smoke. C represents if they get lung cancer. So the event of them smoking and getting cancer is 0.05. Them smoking and not getting cancer is 0.2. Not smoking and getting cancer will be 0.03. Not smoking and not getting cancer would be 0.72. Organize the above information in a two-way table below. Okay, so they said smoking and getting cancer is 0.05. Smoking and not getting cancer would be 0.2, which if we add those together would give us a total of 0.25. Next information, doesn't get smoke, that shouldn't say get smoke, doesn't smoke and gets cancer is 0.03. So that would go right here. So if I add those together, that would be 0.08. And then doesn't smoke and doesn't get cancer would be 0.72. So if we add these down, this would be equal to 0.92. Adding across would be 0.75, which makes sense because both the row and the column of totals equals 100%. Okay, part B, if someone in this population is a smoker, what is the probability that she or he will develop lung cancer? So essentially saying what's the probability of C given M? So that would be the probability that they, M and C, so they smoke and get cancer, divided by the probability that they smoke. So that would be C and M would be that 0.05 divided by just smoking would be 0.25. So 0.05 divided by 0.25 would be 1/5 or 0.2. Part C, compare the probability of C given M to the general probability that an individual develops lung cancer C. So essentially saying, how does P of C given M compare to the probability of just C? This looks just like our independence formula. So that's likely what they're looking for us to comment on. Okay, so the probability of C given M would be equal to C given M. So out of the total, out of total smokers, that's what we just found, that we got 0.2. The probability of getting cancer, P of C, is this 0.08. So these are not the same, meaning that these are dependent events. So we see of those who smoke, there's a 20% chance of getting cancer. Just based upon, like, out of everybody, there is an 8% chance of getting cancer. So they are dependent events. Smoking affects the outcome of getting cancer. Okay, part D, if someone in this population gets lung cancer, what is the probability that she or he is a smoker? That is the probability of M given C. So that would be the probability that they smoke and have cancer divided by the probability that they have cancer. So smoking and cancer, we have said that that was equal to 0.05 divided by the probability of them getting cancer, looking back at our two-way table, would be 0.08. Which would reduce to be 5/8 or 0.625. So if we change it to a percent, it would be about 62.5%. Okay, part E, compare the probability of M given C to the general probability that an individual is a smoker. What do you notice? Again, we're just making that comparison between the two probabilities. So the probability of M given C, we just found that to be 0.625, whereas the probability of just smoking, so M, was 0.25. So it's roughly 3 times higher. Maybe a little bit less than that. So knowing that the person has cancer, because that's our given, it is almost 3 times as likely that the person is a smoker. fancy way of saying that these are dependent events. Okay, and that wraps up this review. Go ahead, rewind, pause if you need to rewatch any of it.